What if we could see a disaster coming before it happened? Well, that's exactly what we're diving into today. We're going to unpack the AI that's making this possible, predicting these huge failures before they even have a chance to start.
It's a really powerful question, isn't it? I mean, just think about it for a second. Imagine a world where we're not just reacting to a crisis after the fact, but we're actually seeing it coming, maybe days, weeks, or even months ahead of time. That's the promise here, and that's what we're going to explore.
Look, the hard reality is that complex systems, well, they fail all the time. We're talking about everything from jet engines to massive industrial machines, and hey, even the complex biological systems inside our own bodies. And when they go wrong, the consequences can be, well, truly catastrophic. But, and this is the really exciting part, there's a kind of quiet revolution happening right now in labs and research centers all over the world. Scientists and engineers are putting together this powerful new toolkit. And it's a toolkit that uses AI to give us this incredible, almost unprecedented ability to see into the future of these systems. So you know what? Let's open up that toolkit and see what's inside.
All right, first up in the toolkit, we've got this massive upgrade to how AI even thinks. And we're not just talking about making it faster. No, we're making it fundamentally smarter. Smarter about how the real physical world actually works. You can almost say AI is getting a physics degree.
So what does that actually mean? Well, it's this idea called physics-informed AI. Think about it like this. A regular AI might see temperature data going up and say, hey, something might fail. But a physics-informed AI, it understands the laws of thermodynamics. It knows why that temperature rise is a huge red flag for material fatigue. And that makes its predictions way, way more reliable. And this really breaks it down perfectly. Your standard AI, it's kind of like a student who just crams by memorizing all the exams. Yeah, it's great at spotting patterns it's seen before. But a physics-informed AI? This one has actually read the textbook. It gets the underlying principles, and that means it can make much more accurate predictions, even in totally new situations, or when it doesn't have a ton of data to work with.
And listen, this isn't just some far-off theory. This is happening right now. You've got researchers like Wang and their team applying this to predict fatigue in engine parts, literally blending AI with the physics of how tiny cracks grow. Then you've got people like Temraz using it to help robots figure out what's wrong with themselves. The big takeaway here is this tech is already in the real world.
Okay, so let's grab the next tool from our kit. This one tackles a really big problem in AI. It's all about prying open that infamous black box. Because let's be real, a perfect prediction is pretty useless if you have no idea how the AI got there, if you can't trust it.
And that's the fundamental issue with so much of today's most powerful AI, right? It can spit out this amazingly accurate answer, but the why behind it is all locked up inside this complicated, murky black box. And if you are a human who has to make a critical decision based on that answer, well, that's just not going to fly.
There's this quote from researcher Moreno Sanchez, who, by the way, developed an AI to predict heart failure that just hits the nail on the head. Transparency is vital to engender trust. That's it. That says everything. For an AI's insight to actually be used, a human expert has to be able to believe in it.
So how do you build that trust? Well, that's where this whole field of explainable AI, or XAI, comes in. Think of it like an interpreter for the AI. It works kind of like this. Step 1, the main AI makes its call, high risk of failure. Then step 2, the XAI tools dig in and analyze how it made that decision. And finally, step 3, it translates all that complex techno-jargon into plain English a person can actually use. Something like, hey, the risk is high because sensor B is picking up a specific vibration that always happens right before this part breaks. And that is why this is so critical. Seriously, would a doctor change a patient's life-saving medicine just because some algorithm they don't understand told them to? No way. Would an engineer ground an entire fleet of airplanes based on a black box's gut feeling? Of course not. They absolutely have to understand the why before they can act with any kind of confidence.
All right, on to tool number 3. So we've got an AI that's smart and an AI that's transparent. Now let's talk about giving it a complete 360-degree view of everything that's going on. We're talking about giving our systems a truly holistic health check.
In the past, trying to predict a failure often meant looking at just one stream of data, like maybe some sensor readings. But today's AI, it is so much more sophisticated. It literally fuses together data from every source imaginable. It's combining maintenance logs that are written in plain English with live data streaming from sensors with old performance reports. And when you put all that together, you get this incredibly rich, complete picture of a system's health. Work by Ameda and their team on aircraft records is a perfect example of this in action.
And this all-seeing approach is popping up everywhere. In aviation, it's giving that total health assessment for an aircraft. In medicine, you see it in research from folks like Vertiman's team, enabling continuous monitoring for things like respiratory failure. In heavy industry, it's spotting tiny structural problems before they have a chance to become huge, catastrophic ones. It really is about seeing the whole system, not just one little piece.
And that brings us to our final tool. And honestly, this might just be the most powerful one in the whole toolkit. It's about creating what you could call the ultimate dream team. We're talking about combining old school, tried and true statistics with the power of new school AI.
So this table lays it out pretty clearly. You've got your traditional statistical models over here. They're solid, we understand them, but yeah, they can be a bit rigid. Then over here you have AI, deep learning. Super flexible, amazing at finding patterns nobody else can see, but it needs a ton of data and can be that black box we talked about. So what do? You create hybrid models. You smash them together to get the best of both worlds, the solid foundation of statistics and the incredible flexibility of AI.
And what's so powerful about this is you get predictions that are both incredibly smart and grounded in reality. But maybe the most important thing, and researchers like Pasha Zanussi have shown this, is that these models can actually tell you how uncertain they are. The AI doesn't just say, hey, this might fail. It says, this might fail, and I'm 95% confident about that. That's a game changer.
So when you take all four of these incredible tools and you put them all together, something really transformative starts to happen. This future that we've all talked about, where our most critical systems, from our infrastructure to our own health, are proactive, self-managing, and just resilient, that's not science fiction anymore. It's actually becoming an engineering reality.
So let's do a quick recap of this revolutionary toolkit we've just opened up. What do we have? We've got smarter AI that actually gets physics. Check. We've got transparent AI that people can trust and work with. Check. We've got an all-seeing AI with that complete 360-degree view. Check. And to top it all off, we have hybrid AI that's both super robust and incredibly flexible. That's a pretty powerful set of tools.
You know, this signals a really fundamental shift in how we think about this stuff. For decades, the big question has always been, can we predict failure? But with the tools we've just looked at, that's not really the question anymore. The real question, the much bigger and more profound question we have to start asking ourselves is, what does a world without unexpected, catastrophic failure actually look like?